of just high energy radiation. It's not high energy radiation is not a monolithic thing. Different wave bands influence different parts of the planetary atmosphere. So we also saw this with David Wilson's talk and a few others. I just want to compare really quick to put everybody on the same basis. A solar type star and a red dwarf star. So the quiet sun is shown here in black. Red dwarf, which is actually GJ832, which was just in the previous talk, was one of my like top 4 favorite M dwarfs. And so we can break these things down into different UV bands, the near UV, the far UV, and the extreme UV. This is a linear plot, so X-rays are actually just squished off to one side. But again, each of these bits of the stellar spectrum have a different impact. So let me first talk about the far UV and the near UV. So a couple of talks this week have talked about the photochemical impacts of this. Let me just drive this home by showing one example from a paper by Vicky Meadows. So this is imagining Prox B in orbit around actual Proxima Centauri versus that same planet orbiting the sun, right? And you see the big difference between the yellow curve and the purple curve is the difference in the methane photochemistry driven by the difference in the stellar UV radiation, largely the ratio of the far UV to near UV. So this can drive big abundance differences in the atmosphere that we may detect someday, and including the production of false positive biomarkers. And so this was a big topic of discussion. If we'd have had a Know Thy Star -1 that was in like 2013 or 2014, this would have been a big topic. And if I were giving this talk back then, this is kind of where the talk would stop. At about the same time, though, we were getting a lot of studies on atmospheric retention around these same red dwarfs that JWST was going to eventually characterize. And so, flash forward to 2022, 2023, 2024, and we're finding that many of these rocky planets around red dwarfs are consistent with the presence of no atmosphere, possibly driven by extreme mass loss and probably related to the very violent properties of their host stars. So this is just one example. This is L9859 from NIRSPEC showing the consistently flat transmission spectrum. I picked this paper as one of the many that are now coming out because it has also a nice prediction of what we might see with MIRI and further into the infrared. And I want to use this as a pitch for the Rocky World's DDT program that is getting started now, where we'll collect, it's not quite clear, but something like 15 mid-infrared photometric observations of rocky planets to assess which of them may be able to retain atmospheres. So anyway, so now that we're talking about the lack of atmospheres, we need to talk about a different part of the host star spectrum. So we're going to focus now on the EUV and the X-ray. This is really what drives the atmospheric ionization. Once we drive a lot of ionization in the atmosphere of a planet, those liberated photoelectrons take their kinetic energy and turn that into heat. The planet's atmosphere puffs up, and if that happens too dramatically, we can lose a lot of the atmosphere to space. So a lot of the times when you see this in the literature, you'll see it as combined X-ray EUV, this thing we call XUV. So I wanted to stop and actually talk about how XUV is also not just a monolithic thing, and X-rays and EUV play distinct roles. So this plot is a plot of the photoelectron production rate normalized to the peak, shown as a function of wavelength and altitude in a representative Earth-like planet's atmosphere. So you see the X-rays down there on the short side, the short wavelength end, and primarily they deposit the majority of their photoelectron energy below about 100 kilometers. Whereas the EUV deposits most of its energy at higher up in the atmosphere. And so let's take a look at some of the differences here. So to start with, the photo absorption cross sections for all of the key molecular species, CO2, nitrogen, molecular nitrogen, they all peak very strongly in the extreme ultraviolet. In addition, what this plot is really showing is that the EUV photons are absorbed in those lowest density, highest parts of the atmosphere. Park Lloyd had a nice plot showing this in the context of corpuscules the other day. And so the X-rays are absorbed deeper. The radiative losses are much higher, and so they actually play a smaller role in the heating. And then on top of which, just there are way more EUV photons in a given star than there are X-ray photons. So noting that for the very youngest, most active stars, there may be a higher X-ray luminosity, but there are more EUV photons in every cool star. So let's put this all now in the context of the cosmic shoreline, right? This is a popular way to think about atmospheric escape now, where we balance the escape velocity, essentially the ability for a planet to hold on to its atmosphere gravitationally on the x-axis, with the XUV irradiation on the y-axis. So this is the cumulative XUV radiation. So this has a couple of parts, and I want to break this down individually. So when we talk about cumulative, right, that means that we're integrating the area under the curve of the entire XUV history of the star. So I'm going to really focus now on what are the EUV properties of the star based on this discussion we just had about there really being the most efficient atmospheric escape drivers. So here is a plot of the bolometric luminosity normalized EUV history of solar type stars. So this actually is something new that we're doing now because this quantity is actually really not very well known. So keep this in mind, right? And this is for solar type stars, but now we want to compare this to what we might be expecting for red dwarf stars. So if we look at the EUV history in the same units of sort of intermediate mass M-type stars, maybe M2, M3 stars, you'll get a plot that looks something like this, right? The things that jump out at you right away is that the M dwarfs are spending a way longer time in that saturated regime we've heard about, and they also have a different decline slope. If we were talking about late M dwarfs, fully convective M dwarfs, that saturated time would maybe go out another factor of 2 or 2.5 times longer. So if you put all those differences together, you're talking about maybe a factor of 10 difference in the lifetime integrated history. And so when you come back to our M dwarf driven cumulative X-ray irradiation plot, we need to account for that difference because the concept of the habitable zone is all driven by solar X-ray observations or solar type star X-ray observations. So when we want to factor in the uncertainty converting that to an M dwarf, we are going to introduce probably about a factor of 10 uncertainty. So we might want to then ask ourselves, like, that's the history. What about just knowing the EUV flux from any star, M-type or otherwise? So here's an example. This is a spectrum, a very broad panchromatic spectrum of Proxen, right, our nearest M dwarf neighbor. And the size of the shaded region indicates the relative uncertainty in the flux in those wavelength bands. And I'll mention again at the end, but we have so few direct EUV observations that we rely on scaling laws to estimate what the EUV fluxes are. So if I just want to blow up the EUV part of the spectrum, those different colored lines and that solid black line are different widely used scaling relationships to estimate what the EUV flux is for other stars. The one on the top is based on X-rays. The one on the bottom is based on UV data alone. And again, those are both papers with hundreds of citations in the literature. But you can see that at various parts of the EUV spectrum, they're discrepant by over 2 orders of magnitude, right? And so that's going to have a huge impact on the total mass loss rate you would expect. So if we propagate those forward in a simple one-dimensional mass loss calculation, we can see that if we use this really aggressive EUV flux that's based on X-rays, we could be losing maybe tens of Earth oceans of atmosphere over the course of 4.5 billion years. But if we use this much more conservative or lower EUV flux, we would be losing maybe even less than 1 Earth ocean over the course of the planet's lifetime. So the differences really make a big difference. And I'll come back and I'll end on that topic in just a second, because so we fold this into our understanding of the cosmic shoreline study here. So we've already added a factor of 10 uncertainty for the history difference, but we just showed that you can also get another factor of 10 uncertainty difference just because you plain old don't know what the EUV flux is. And so now we're really talking about almost 2 orders of magnitude uncertainty in either direction on where we place things on this cosmic shoreline diagram. But wait, it's actually worse. To bring back GJ832 again, this is a figure from Park Lloyd from several years ago, what he was talking about at Know Thy Star 1. And I just still one of my favorite things to show, right? But what we found is through these studies like mussels and other spectacularly derived acronym projects, that these inactive M dwarfs are still very UV active. So we did a study a few years ago using Barnard star, probably the oldest, the oldest M dwarf with a pretty good age. And so we studied the atmospheric loss from both thermal and non-thermal processes for the quiescent version of Barnard star. And this is an ion escape simulation. This is based on some software that's developed for studying atmospheric loss at Mars. And we see that comparing the quiescent mass loss from Barnard star versus the Earth-Sun system, it's pretty similar. But when we include the flares that we observe, even on this very inactive object, we see that we can lose tremendous, essentially, there's no way an atmosphere is going to survive on a planet like this. So when we think about putting this on the cosmic shoreline, right, we also probably need to think about stochastic uppers to this process. And this isn't even including the particles. So in my my last 2 minutes here, the thing I want to really end on is this question of like, how do we even know that our estimates are any good? So this is a history of solar EUV knowledge. So that's the actually observed EUV. Those are the 4 solar type stars that inform everything we know empirically about EUV stars. Those are the 4 M dwarfs that are all in the saturated regime that have EUV measurements. So if we really want to start to get to the histories and the actual what is the present day knowledge, we're going to have to measure these stars directly. And so that's where we get to the escape mission concept. So this is an EUV, FUV spectroscopic mission that's been proposed to the 2015 SMEX or 2025 SMEX round to essentially map out empirically both the present day and the history of EUV from all types of nearby cool stars. At the same time, we'll also get to measure all of the CMEs that Park talked about using this coronal dimming technique. So, and we're going to demonstrate all of these things on a technology demonstration mission that David Wilson talked about. So I'm about out of time, so I'll just go ahead and put up my conclusions and take questions. Thanks a lot.
All right, we do have time for one question.
Hey, Kevin, this is David. Really nice talk. So one of the plots where you were talking about how long the M dwarfs stay in the saturated range of the. So is that a relatively, as you move through the M dwarf sequence, does that saturated, the time frame of the saturated range, does that change smoothly across the M dwarf sequence, or is it basically about the same across all of the M dwarfs?
Yeah, I think what we can say for sure is that the massive M dwarfs stay in the saturated regime for a shorter period of time, and the later M dwarfs live there longer. I don't think we really have enough data to understand exactly how that changes, particularly if it really changes smoothly across the completely convective divide. It's definitely, you can lump them into 2 categories, but I just don't think we have enough data right now. And again, bearing all those caveats in mind about all the scaling relations involved.
Thank you.
Awesome. All right. Thank you, Kevin, very much.